This video is of why faster-than-light travel, the single most beloved idea in the entire history of science fiction, the dream that has sold 1 billion movie tickets and kept 1,000 novelists employed and convinced generations of children that the stars were reachable within a lifetime, would not just be physically difficult, or dangerously expensive, or technologically beyond our current means. It would not merely strain the laws of physics, the way a very heavy truck strains a bridge. It would dissolve the structure of cause and effect so completely, so irreversibly, and so mathematically certainly that the universe as a coherent, navigable, comprehensible place would cease to exist. Not metaphorically, not as a dramatic way of saying it would be really bad. Literally, the logical architecture that makes reality a reality, rather than an undifferentiated noise of events with no before and no after and no meaning, depends entirely on a single number: 299,792,458 meters per second. And the moment you exceed it, even once, even by a hair, the entire structure comes apart. Before we spend the next hour walking through exactly how and why that happens, and before we go through the physics of warp drives and wormholes and tachyons and quantum entanglement and all the clever proposed workarounds that have been examined and found wanting, if the idea that a speed limit could be the foundation of all meaning in the universe sounds like the kind of thing you want to think about carefully, hit the like button right now and subscribe to this channel, because this is exactly the kind of science we live for here. The science that does not just add a fact to your mental database, but changes the lens through which you see everything. Let us start at the very beginning, and the beginning here is a specific year, a specific place, and a specific young man who was about to rewrite the terms of reality. The year was 1905, and a 26-year-old patent clerk named Albert Einstein was working in Bern, Switzerland, spending his days evaluating patent applications and his evenings and lunch breaks thinking about the deepest problems in physics. He had no university position, no laboratory, no graduate students, and no funding. He had a desk, some paper, and a mind that was quietly rearranging the foundations of human understanding. In that single year, 1905, Einstein published 4 scientific papers, each of which would have made a lesser physicist's entire career. One of them introduced the concept of light quanta, which became the foundation of quantum mechanics. One explained Brownian motion in a way that confirmed the atomic hypothesis. One introduced the famous relationship between mass and energy, E equals mc squared. And one the paper titled On the Electrodynamics of Moving Bodies, submitted to the German journal Annalen der Physik, and published in September of that year, introduced the special theory of relativity to the world. The special theory of relativity is built on 2 postulates, 2 foundational assumptions that Einstein stated clearly at the beginning of his paper and then followed with ruthless mathematical rigor wherever they led. The first postulate is this: the laws of physics are the same in all inertial reference frames. An inertial reference frame is any frame of reference that is not accelerating a spaceship coasting through empty space, a laboratory sitting still on the surface of a planet, a train moving at constant speed along a straight track. Einstein's first postulate says that no experiment you can perform inside any of these frames will tell you whether you are moving or standing still, because the laws of physics behave identically in all of them. There is no absolute rest. There is no cosmic address against which your velocity can be measured. Motion is always relative to something else. The second postulate is the one that breaks your intuition and refuses to let you have it back. The speed of light in a vacuum is always 299,792,458 meters per second. Regardless of the motion of the source emitting the light, and regardless of the motion of the observer measuring it. This seems absurd at first, because everything else in human experience works differently. If you throw a ball at 30 kilometers per hour from a car moving at 100 kilometers per hour, someone standing on the roadside sees the ball moving at 130 kilometers per hour. The speeds add. But if you shine a flashlight from that car, the light from the flashlight does not move at the speed of light plus 100 kilometers per hour. It moves at exactly the speed of light. From the perspective of the driver, from the perspective of the bystander on the road, From the perspective of someone on the moon watching through a telescope, always and exactly the same number. This is not a mathematical trick. This is what experiments show. And the consequences of taking this seriously, of following the mathematics wherever it goes without flinching, are among the most dramatic in the history of science. The speed of light as a finite, measurable quantity had been on the radar of physics for a long time before Einstein came along and made it the center of everything. The first real measurement of its speed came in 1676 from a Danish astronomer named Ole Romer, who was working at the Paris Observatory under the patronage of King Louis XIV. Romer was studying the orbit of Io, one of Jupiter's 4 large moons, and he noticed something curious. The timing of Io's eclipses behind Jupiter was not consistent. Sometimes Io disappeared behind Jupiter earlier than predicted, and sometimes later, and the discrepancy correlated with Earth's position in its orbit around the Sunday. When Earth was moving toward Jupiter, the eclipses came slightly early. When Earth was moving away, they came slightly late. Romer's explanation was that light takes time to travel, and that the variation in timing reflected the varying distance light had to cover between Jupiter and Earth, depending on where Earth was in its orbit. He used this to calculate a value for the speed of light, and while his answer was about 26% slower than the correct value, a reasonable error given the instruments available in the 17th century, the critical insight was established. Light does not travel instantaneously. It moves at a finite, measurable speed, and that speed is very, very fast, but not infinite. By the middle of the 19th century, the theoretical framework catching up to Romer's observation had been built by James Clerk Maxwell, a Scottish physicist who is among the most important scientists who ever lived and who is not nearly as famous as he deserves to be. In 1865, Maxwell published his unified theory of electromagnetism, a set of equations that described how electric and magnetic fields behave and how they produce each other. Hidden inside those equations was a prediction: electromagnetic disturbances, light, radio waves, anything in the electromagnetic spectrum propagate through empty space at a speed determined by 2 constants, the permittivity of free space and the permeability of free space. When you plug in the measured values of those constants, the speed that falls out of the mathematics is approximately 300,000 kilometers per second. Maxwell recognized this number immediately. It was the speed of light. What Maxwell had discovered, without quite framing it that way, was that light is an electromagnetic wave, and that its speed is not a property of the source or the medium, but a built-in feature of the structure of electromagnetic fields themselves. The speed was in the equations. It was baked into the fabric of electromagnetism. But this created a problem that physicists at the time were acutely aware of. If light has a definite speed, it must be a speed relative to something. Sound waves travel at about 340 meters per second, relative to the air they propagate through. What was the medium that light propagated through? Physicists of the 19th century called it the luminiferous ether, from the Greek word for the pure air, supposedly breathed by the gods, and they assumed it filled all of space as an invisible, weightless, perfectly transparent substance through which light moved. The speed of light, they believed, was 300,000 kilometers per second relative to the ether, which meant that Earth, moving through the ether as it orbited the Sun, should experience a kind of ether wind, and that this ether wind should cause light traveling in different directions to have measurably different speeds relative to Earth. In 1887, 2 American physicists named Albert Michelson and Edward Morley set out to measure this difference. Michelson had already built the most sensitive light-measuring instrument in the world, an interferometer that could detect tiny differences in the travel time of light beams sent in different directions. He and Morley set it up in a basement at what is now Case Western Reserve University in Cleveland, mounted the whole apparatus on a massive stone slab floating on mercury to isolate it from vibrations, and ran the experiment. The result was one of the most consequential negative results in the history of science. There was no ether wind. The speed of light was the same in every direction, regardless of Earth's motion. The aether did not exist. The Michelson-Morley experiment did not directly produce special relativity that took another 18 years, and Einstein's particular genius, but it shattered the conceptual framework that physicists had used to make sense of light's propagation, and it demanded a new framework. The old scaffolding of absolute rest and a universal medium was gone. Something new was needed to explain why light always moved at the same speed for every observer. Einstein provided that new framework in 1905, and the something new was the special theory of relativity, with all its spectacular and sometimes terrifying consequences. Now, to understand why the speed of light is not just fast, but the absolute maximum speed in the universe, you need to meet the Lorentz factor. This is a quantity that appears throughout special relativity, named for the Dutch physicist Hendrik Lorentz, who derived it before Einstein, but interpreted it differently. The Lorentz factor, written with the Greek letter gamma, equals 1 divided by the square root of 1 minus the ratio of your velocity squared to the speed of light squared. At low velocities, the speeds of cars, planes, even rockets, this factor is extremely close to 1, and its effect is too small to notice. A passenger jet traveling at 900 kilometers per hour has a Lorentz factor of approximately 1.000000000004, which means the effects of special relativity on that jet are real but utterly negligible for any practical purpose. But as velocity increases toward the speed of light, the denominator of the Lorentz factor, that square root of 1 minus v squared over c squared, shrinks towards 0, and as the denominator shrinks towards 0, the Lorentz factor itself grows toward infinity. At 90% of the speed of light, gamma is about 2.3. At 99%, it climbs to about 7.1. At 99.9%, it reaches about 22.4. At 99.99%, about 70.7. At 99.9999991%, which is how fast protons travel in the Large Hadron Collider at CERN, the Lorentz factor is approximately 7,460. The energy required to accelerate a massive object scales with this factor. The faster you want to go, the higher the Lorentz factor, and the more energy you need. And the relationship between energy needed and velocity remaining is not linear, but exponential in its relentlessness. Getting from 99% to 99.9% takes far more energy than getting from 0 to 99%. Getting from 99.9 to 99.99 takes far more than that. Each successive decimal place of closeness to c demands a multiplicative increase in energy. At the limit, exactly at c, the Lorentz factor is infinite, and the energy required is infinite. No finite energy source, no matter how exotic or advanced, can supply infinite energy. The speed of light is not a wall that advanced engineering might eventually punch through. It is a mathematical singularity. Infinity is not a very large number that might someday be achievable. It is infinity. The experimenters at CERN demonstrated this directly and precisely. The Large Hadron Collider, built in a circular tunnel 27 kilometers in circumference beneath the border between Switzerland and France, accelerates protons to energies of up to 6.5 trillion electron volts per beam. At these energies, the protons are moving at 99.999999% of the speed of light. The energy required at each step of the acceleration follows the Lorentz factor formula with extraordinary precision. Every time the LHC has been upgraded to push protons closer to c, the energy costs have matched special relativity's predictions exactly, with no deviation detectable by any instrument ever built. The universe has been asked, in the most direct possible way, whether the speed of light really is the limit, and it has answered yes, with every decimal place of experimental precision available. Now, here is where the story takes its first sharp turn toward the genuinely alarming, because most people who think about FTL travel think about it as an engineering problem, a fuel problem, an energy problem. The real problem is not that we lack the energy. The real problem is what the mathematics of special relativity does to cause and effect when you exceed c, and that problem is not engineering, it is logic. To see why, you need to understand the concept of the light cone, which is one of the most useful and important ideas in all of modern physics, and once you see it clearly, you cannot unsee it. Imagine a graph where two of the axes represent spatial dimensions, say left, right, and front, back, and the third axis represents time, running upward. Every event in the universe can be plotted as a point on this graph, a point in space at a moment in time. Now, take any one event, call it Event A, and ask, what other events could possibly have caused it? Only events from which a signal moving at or below the speed of light could have reached Event A in time. If you draw all the points from which a light signal could have just barely arrived at Event A, those points form a cone, pointing downward in time from Event A. Physicists call this the past light cone. Everything inside the past light cone could have been a cause of Event A. Now ask the opposite question. What events could Event A possibly influence? Only events that a signal moving at or below the speed of light could reach from Event A. Draw those points, and they form a cone pointing upward in time from Event A. This is the future light cone. Everything inside it could be an effect of Event A. What about everything outside both cones, the events in what physicists call the space-like region? These events are separated from Event A by a distance so large, relative to the time between them, that not even light could make the journey. These events cannot be causes of Event A, and Event A cannot cause them. They are causally disconnected, sitting outside the light cones, unreachable by any physical influence traveling at or below c. Causality, the principle that every effect has a cause that precedes it in time, is perfectly safe within this structure. Send any signal at any speed up to c, and every observer in every possible reference frame, moving at any possible sublight velocity in any possible direction, will agree on the time ordering. The signal was sent before it was received. That consensus across all frames is the mathematical expression of causality, and it is rock solid as long as nothing exceeds c. The moment something exceeds c, that consensus evaporates, and this is not a subtle or borderline effect. It is dramatic, clean, and unavoidable. The Lorentz transformations, the mathematical rules that Einstein derived for converting coordinates between reference frames moving relative to each other, the transformations that have been tested and confirmed in thousands of experiments, tell us something stark about space-like separated events. For any two events separated by a space-like interval, meaning any two events that could only be connected by a signal faster than light, there always exists a valid reference frame in which the events occur in the opposite time order. What is cause in one frame is effect in another. What is sent before received in your frame is received before sent in mine. Let that settle in for a moment, because it is easy to read it and move on without fully absorbing it. If a signal travels faster than light, any signal, any message, any amount of information whatsoever, then there will always exist some observer, somewhere in the universe, moving at some perfectly ordinary, perfectly sublight velocity in some perfectly ordinary direction, for whom that signal arrived before it was transmitted, not appeared to arrive before it was transmitted. Actually, physically, in a frame that is just as valid as any other, arrived before it was sent, and that observer's measurement is not wrong or distorted, it is as real as yours. This specific consequence has been worked out in precise mathematical detail, and it has a name, the tachyonic antitelephone. The concept was formalized in a paper published in 1970 inches, the journal Physical Review D, by Gregory Benford, David Book, and William Newcomb. The argument goes like this. Imagine two space stations, Station Alpha and Station Beta, equipped with faster-than-light communication devices. The stations are moving relative to each other, which is an unremarkable condition. Everything in the universe is moving relative to everything else. Station Alpha sends an FTL message to Station Beta. Because of the space-like separation and the relative motion of the stations, there is a reference frame, a perfectly valid, physically meaningful reference frame in which Station Beta receives the message before Station Alpha sent it. Now, Station Beta responding promptly as any good communication station should, sends an FTL reply back to station alpha. This reply, traveling FTL in the direction back toward alpha, combined with the relative motion of the stations, can arrive at station alpha before station alpha sent the original message in the first place. Not just before station beta replied, before station alpha sent the original message. Station alpha now has, in its hands, a reply to a message it has not yet composed. This reply might contain information, "Yes, we received your message, we'll have the supplies ready," that informs station alpha's decision about whether to send the original message. Perhaps the reply says, "Do not send supplies, we are fine." Station alpha, reading this reply before it has sent anything, decides not to send the original message. But if it does not send the message, station beta never receives it, and therefore never sends the reply that told station alpha not to send anything. The message was never sent, the reply was never sent, but station alpha received the reply. The sequence of events is logically self-contradictory. The universe has no consistent answer to the question of what happened. This is not science fiction plotting. This is the output of combining faster-than-light signaling with Lorentz transformations that have been tested to extraordinary precision in every particle accelerator ever built. The conclusion is mathematical and unavoidable. Faster-than-light signaling implies the possibility of causal loops, and causal loops are logically incoherent. The 2011 Opera experiment at CERN is the most vivid real-world illustration of how seriously physicists take this implication. In September of 2011, researchers from the Opera collaboration, a group spanning CERN in Geneva and the Gran Sasso National Laboratory in Italy, announced a stunning result. Neutrinos sent through the ground from CERN arrived at Gran Sasso, 730 kilometers away, approximately 60 nanoseconds faster than the speed of light would permit. 60 nanoseconds is barely a measure of time that the human mind can grasp. It is 60 billionths of a second, roughly the time it takes light to travel 18 meters. But the claim, if true, would have been the most consequential result in physics since Einstein's 1905 paper. The physics community's reaction was not celebration. It was intense, almost anxious scrutiny, because the community understood exactly what a confirmed FTL result would mean. Not a new speed record, but the demolition of the entire theoretical framework of modern physics. Every physicist who worked on special relativity, quantum field theory, the Standard Model, general relativity, all of it would need to be rebuilt from scratch. The peer review was merciless and exhaustive. By May of 2012, the source of the anomaly was found. A faulty fiber optic cable connection between the GPS receiver and the master clock was introducing a systematic timing error, and a separate oscillator component was also found to have been malfunctioning. Both errors conspired to make the neutrinos appear faster than they were. When the hardware was repaired and the experiment run again, the neutrinos arrived precisely on time. The speed of light held. The relief among physicists was genuine and palpable, not because scientists are conservative or afraid of new physics, but because they understood what the alternative would have meant for everything they knew. Now let us spend significant time on quantum entanglement, because it is the single most commonly cited argument for the possibility of FTL communication, and it deserves a careful and thorough dismantling, not because entanglement is unimportant, but because it is among the most genuinely strange phenomena in all of physics, and its strangeness deserves to be understood correctly, rather than misappropriated. The story of quantum entanglement begins in 1935 with a paper authored by Albert Einstein, Boris Podolsky, and Nathan Rosen, the paper known ever since by the initials EPR. The paper was Einstein's attempt to demonstrate a fundamental flaw in quantum mechanics. Einstein had deeply resisted the probabilistic, indeterminate interpretation of quantum mechanics championed by Niels Bohr and his Copenhagen school, and the EPR paper was his most sophisticated attack on it. The argument went like this. Quantum mechanics predicts that two particles can be prepared in a correlated state, such that measuring one particle instantly determines a property of the other, regardless of how far apart they are. If you measure the spin of one entangled particle, and find it is spin up along a given axis, you instantly know the other particle's spin is spin down along that axis without measuring it directly. Einstein found this deeply troubling. Either the two particles were communicating instantaneously across arbitrary distances, which he found physically absurd and called spooky action at a distance, or the particles had always carried predefined values for their spins, hidden variables. Information encoded in the particles at the moment of their creation and quantum mechanics was simply incomplete, failing to describe that pre-existing information. Einstein preferred the hidden variables option. He did not believe in spooky action at a distance. He believed in locality, that events here cannot be instantly influenced by events there. And he believed in realism, that physical properties have definite values, whether or not they are being measured. The EPR paper was meant to force a choice. Either quantum mechanics was non-local, which was unacceptable, or it was incomplete, missing some deeper local realistic theory. The question sat largely unresolved for nearly 30 years, regarded by many physicists as an interesting philosophical puzzle without obvious experimental consequence. Then, in 1964, an Irish physicist named John Bell did something remarkable. He found a way to turn it into an experimental question. Bell's theorem showed that if particles carried hidden variables of any kind that obeyed local realistic constraints, any theory that was both local and realistic in Einstein's sense, then the correlations between measurements of those particles would be limited in a specific, mathematically provable way. The correlations could not exceed a certain value, now called a Bell inequality. Quantum mechanics, on the other hand, predicted correlations that violated this limit. The two theories made different numerical predictions. An experiment could distinguish between them. In 1982, Alain Aspect and his group at the Institut d'Optique in Paris ran that experiment. They produced pairs of entangled photons and measured their polarizations under conditions carefully designed to close as many loopholes as possible. And the results unambiguously violated Bell's inequalities exactly as quantum mechanics predicted, and exactly as no local hidden variable theory could explain. The correlations were real, they were non-local, and they could not be explained by any pre-existing information stored in the particles. Einstein was wrong about hidden variables. Spooky action at a distance, of a sort, is real. Aspect shared the Nobel Prize in Physics in 2022 with John Clauser, who had run earlier versions of the test, and Anton Zeilinger, who extended the experiments to close additional loopholes and push quantum entanglement toward applications in quantum communication and cryptography. The Nobel Committee's citation described their work as establishing experimental confirmation that the universe is genuinely non-local in the quantum mechanical sense. And yet, and this is the crucial point that popular accounts consistently fail to communicate with sufficient clarity, quantum entanglement cannot be used to send information faster than light. This is not a limitation that better technology might overcome. It is not a practical constraint waiting to be engineered away. It is a fundamental feature of how entanglement works, proven rigorously in what physicists call the no-communication theorem. Here is why. When you measure your entangled particle, you get a random outcome. You might get spin up or spin down, and there is no way to control, predict, or influence which one you get. 50-50, genuinely random. Your distant partner's particle collapses into the corresponding correlated state the instant you measure yours, but their result is also random. They get spin up or spin down, 50-50, with no control over the outcome. Only when you and your partner compare results through an ordinary, conventional, slower-than-light channel, a phone call, a radio transmission, a letter, do you discover that your results are correlated. You can see the pattern only after the fact, and only through a classical channel. There is no way to encode a message in quantum entanglement because you cannot control what result your particle gives you. You cannot make it say spin up on demand to communicate a 0, or spin down on demand to communicate a 1. The outcome is random. If you measure your particle 1,000 times with different entangled particles prepared the same way, you get a sequence of random ones and zeros that look like noise. Your partner gets the complementary noise. Neither noise sequence contains any information. The correlation between the sequences is only visible when you put the two sequences side by side, and putting them side by side requires a sublight communication channel. The no communication theorem, proven in various forms by Philipp Eberhard in 1978 and by others subsequently, formalizes this. The density matrix of your partner's particle is unchanged by any measurement you perform on yours. There is literally nothing in the physics of their particle, before you contact them classically, that reveals you made a measurement at all. A complementary obstacle is the no-cloning theorem, proven independently by William Wouters, Wojciech Zurek, and Dennis Diex in 1982. The no-cloning theorem states that it is physically impossible to create a perfect copy of an arbitrary unknown quantum state. This closes off a potential backdoor to FTL. If you could clone an entangled particle and make many copies, you might be able to measure the copies multiple times to statistically determine which way the distant partner collapsed the original. But you cannot make those copies. The no-cloning theorem forbids it, and the same quantum mechanics that produces entanglement also produces this prohibition. The universe's rules are self-consistent in a way that blocks every obvious attempt to use quantum weirdness for FTL information transfer. Quantum teleportation is sometimes raised in this context as a counterexample after all. It genuinely does transmit a quantum state from one location to another without the state physically traveling through the intervening space. But quantum teleportation requires a classical channel to complete the process. The sender must transmit two classical bits of information to the receiver before the receiver can reconstruct the teleported state. Without those classical bits, the receiver has no usable quantum state, just half of an entangled pair in an indeterminate state. The classical channel is the bottleneck. The information transfer in quantum teleportation is limited to the speed of that classical channel, which is at most the speed of light. The quantum part is strange and beautiful, and genuinely non-local in a narrow sense, but the usable information transfer is always subluminal. The ER equals EPR conjecture, proposed in 2013 by Juan Maldacena and Leonard Susskind, adds a fascinating theoretical dimension to the entanglement story. ER stands for Einstein-Rosen, the two authors of the 1935 paper on wormholes. EPR stands for Einstein-Podolsky-Rosen, the three authors of the 1935 paper on entanglement. The conjecture proposes that these two phenomena, wormholes and quantum entanglement, are not merely analogous, but are in fact the same phenomenon described in two different ways, that every pair of entangled particles is connected by a microscopic wormhole in the fabric of space-time. The idea is beautiful and has generated enormous theoretical research, particularly in quantum gravity, because it suggests that the geometry of space-time might emerge from quantum entanglement at a fundamental level. But even if ER equals EPR is correct, and it remains a conjecture rather than an established theorem, it does not imply FTL communication. The wormholes connecting entangled particles, if they exist, would be far too small and unstable to transmit information, and they would inherit the same no communication properties from the entanglement side of the equation that they carry from the wormhole side. The deep connection between the two phenomena, if real, means they share the same prohibition on FTL signaling. ER equals EPR is a beautiful idea. It is not a loophole. With entanglement properly understood, let us turn to the most famous serious proposals for faster-than-light travel that have come from within the physics community itself, starting with the one that captured the most public imagination and generated the most serious scientific discussion, the Alcubierre drive. Miguel Alcubierre is a Mexican theoretical physicist who in 1994 was a graduate student at Cardiff University in Wales. In that year, he published a paper in the journal Classical and Quantum Gravity with the deliberately provocative title, The Warp Drive, Hyperfast Travel Within General Relativity. The paper did not propose a technology. It proposed a mathematical solution, a specific geometry of spacetime described within the framework of Einstein's general relativity that would, if it could be physically realized, allow a region of space to effectively travel at any speed relative to distant observers, including speeds far exceeding c. The idea behind it is elegant. General relativity, unlike special relativity, deals not just with flat spacetime, but with curved spacetime, and spacetime can curve in ways that have no equivalent in special relativity. The universe's own expansion, for example, carries distant galaxies away from us at recession velocities exceeding the speed of light, not because those galaxies are locally moving faster than light, but because the space between us and them is growing. This expansion is a feature of space-time geometry, and it is not subject to the speed of light limit that applies to local motion through space-time. Alcubierre's insight was to ask whether a similar effect could be engineered locally, whether a region of space-time could be arranged to move through the universe by the manipulation of the space-time geometry itself, rather than by propelling an object through stationary space-time. His solution described a bubble of flat space-time, a small region where the laws of physics apply normally, where the crew could sit comfortably and experience no acceleration, surrounded by a shell where space-time was being compressed ahead of the bubble and expanded behind it. The bubble would ride this wave of space-time curvature at arbitrarily high effective velocities, like a surfer riding a wave, with the crucial distinction that the surfer and the wave are part of the ocean, while the bubble and its occupants are in locally flat space. Nothing inside the bubble would be locally moving faster than light. From the perspective of the people inside, they would be sitting still while space-time rearranged itself around them. The apparent FTL motion relative to distant observers would be a consequence of the space-time geometry, not of the crew exceeding c locally. This was Alcubierre's clever attempt to be consistent with special relativity while violating its practical implication. The paper generated significant excitement when it was published, and it has been cited thousands of times in the decades since. Alcubierre himself was clear that the paper was meant as a mathematical exploration of what general relativity's equations permit a thought experiment in the tradition of Einstein's own method, rather than an engineering proposal or a claim that the device could actually be built. But the attention it received went well beyond that modest framing. The problems with the Alcubierre drive are numerous, severe, and ultimately fatal to the concept as a practical or even theoretical tool for FTL travel. Let us go through them in sequence, because each one is instructive about a different aspect of the physics involved. The first and most immediate problem is exotic matter. The Einstein field equations, the equations governing how space-time curvature is related to the distribution of matter and energy, tell us that producing the specific geometry Alcubierre described requires matter with negative energy density. Ordinary matter, everything we have ever observed, has positive mass and positive energy density. Negative energy density is not merely an exotic material with unusual properties, it is something that would violate the weak energy condition, one of the fundamental constraints that most realistic physical theories satisfy. A sufficiently negative energy density would cause spacetime to curve the wrong way, the way the Alcubierre bubble requires. But such a substance has never been confirmed to exist in stable, macroscopic quantities. The Casimir effect is the closest analogue available. Two uncharged parallel metal plates placed extremely close together in a vacuum experience an attractive force that arises from quantum fluctuations in the electromagnetic field between them. The energy density of the quantum vacuum between the plates is slightly lower than the energy density of the vacuum outside, and in a specific mathematical sense, this constitutes a negative energy density region. But the amounts involved are infinitesimally small. They cannot be measured with the naked eye. They require specialized equipment to detect at all, and they exist only over microscopic scales. The Casimir effect tells us that nature permits negative energy density in principle, but not in any form that scales up to macroscopic warp bubble maintenance. The energy requirements for the Alcubierre drive, even setting aside the question of whether exotic matter exists at all, were found by early calculations to be staggering beyond imagination. Producing the space-time curvature required for a warp bubble of useful size would demand exotic matter with a mass-energy equivalent roughly equal to the mass of Jupiter, converted entirely to negative energy. The mass of Jupiter, not a nuclear weapon, not a star, but a gas giant planet. Harold Sunny, White of NASA's Johnson Space Center published revised calculations in 2012, refining the shape of the warp bubble to make its energy requirements less catastrophic, and the revised estimates were significantly lower. But even significantly lower than Jupiter mass is not a figure that any conceivable engineering project could approach. The second problem is controllability. The crew inside the warp bubble cannot steer it. Because the bubble is moving faster than light relative to the outside universe, any signal the crew might send to the front wall of the bubble, any attempt to communicate instructions about where to go or when to stop, would itself need to travel faster than light to reach the front wall ahead of the bubble. The crew cannot signal ahead of their own motion because their motion is by definition faster than any signal. Once the bubble is set in motion, the crew inside is a passenger in a vehicle without a steering wheel. Someone outside, stationary relative to the departure point, could in principle have pre-programmed the bubble's behavior, but once activated, the crew cannot adjust course. This is not a minor inconvenience. For a travel device intended to navigate between specific stellar destinations separated by light years, being unable to steer is a rather significant limitation. The third problem is radiation. Quantum field calculations show that a moving warp bubble would interact with the quantum vacuum in a way that accumulates particles at its leading edge. As the bubble travels, it sweeps up quantum fluctuations from the vacuum ahead of it, compressing and energizing them. And by the time the bubble decelerates and stops at its destination, the leading edge has accumulated a concentrated burst of high-energy radiation. The calculations suggest this radiation burst would be lethal to anything at the destination that the bubble was approaching. An interstellar ship arriving at an inhabited planet using an Alcubierre drive would deliver a radiation weapon to that planet before the crew ever got out. The drive is incompatible with the goal of peaceful interstellar visits. The fourth problem, the deepest and most fundamental, the one that connects the Alcubierre drive to the broader story this video is telling, is causality. Even if every engineering problem were somehow solved, even if exotic matter were found in abundance and the energy requirements met and the steering problem solved and the radiation dissipated, the Alcubierre drive would still be a time machine, and a time machine breaks causality, and broken causality breaks reality. This was shown rigorously in a 1996 paper by Alan Everett, who analyzed the causal structure of the Alcubierre metric in detail. Everett found that two observers, each with access to an Alcubierre drive, could cooperate to construct a closed time-like curve, a path through spacetime that loops back to its starting point in time. The construction requires two warp trips at different velocities and in different directions, exploiting the way different reference frames perceive the time ordering of the journeys differently. Neither trip alone produces backward time travel, but the combination, in a universe where two civilizations each have warp drive capability, allows the construction of a causal loop that visits a time before either trip departed. Everett and Roman subsequently showed that this causality violation is not specific to the Alcubierre drive or to extreme superluminal velocities. Any violation of the light speed limit by any finite amount, in any direction, combined with the symmetry properties of special relativity and the existence of multiple observers in relative motion, is sufficient in principle to construct a causal loop. There is no safe FTL, no amount of superluminal travel that is too small to break causality. Even a marginally FTL signal traveling at 1.000001 times c can form the basis of a causal paradox when combined with a second such signal in a different reference frame. Sergei Krasnikov, a Russian physicist, proposed in 1995 a modification called the Krasnikov tube, which involves laying a tube of modified spacetime along a path between 2 points and using it to travel faster than light without the sum of the Alcubierre drive's specific drawbacks. Michael, Pfenning, and L. Ford analyzed the Krasnikov tube's energy requirements and found them even more extreme than the Alcubierre drives, again involving exotic matter in quantities that violate every realistic physical bound. And when two Krasnikov tubes are laid along intersecting paths in opposite directions, they too permit closed time-like curves. The specific mechanism is different from the Alcubierre drive, but the causal conclusion is the same. The pattern here is consistent enough to constitute a general principle. Any mechanism that allows faster-than-light travel, regardless of its specific physical implementation, when made available to multiple observers in relative motion, permits the construction of causal loops. The causality violation is not a side effect of bad engineering that could be avoided with better design. It is a consequence of the mathematical relationship between FTL travel and the Lorentz transformation, and it applies universally. Now let us turn to wormholes, which occupy a different corner of the FTL imagination, and whose story involves one of the most charming intersections of theoretical physics and popular fiction in scientific history. Wormholes, as a mathematical concept, entered physics in 1935 through a paper by Albert Einstein and his assistant, Nathan Rosen, who discovered that the Schwarzschild solution to Einstein's field equations of the mathematical description of the space-time geometry around a non-rotating black hole could be interpreted as describing a bridge, connecting two separate regions of space-time. This is not the popular image of a wormhole as a convenient interstellar shortcut. The Einstein-Rosen bridge is a purely mathematical feature of the vacuum solution to the field equations, and it is dynamically unstable. It forms and collapses so rapidly that not even light can pass through it before the throat pinches off. It is a feature of the mathematical structure rather than a physically usable tunnel. The traversable wormhole, one that could actually be passed through, came much later, and the catalyst for its development was a science fiction novel. In the early 1980s, Carl Sagan, already famous as the host of the television series Cosmos and as one of the world's most beloved science communicators, was writing a novel called Contact, about a radio signal from an extraterrestrial civilization and the first physical meeting between humanity and that civilization. Sagan wanted his protagonist to travel between the stars through a mechanism that was physically plausible, not a magic portal, not a hand-waved convenience, but something that the equations of physics actually permitted. He consulted his colleague Kip Thorne at the California Institute of Technology, who was one of the world's foremost experts on general relativity. Thorne took the question seriously, which is characteristic of his approach to physics. He and his graduate student Mike Morris worked through the mathematics of what a genuinely traversable wormhole would require, and in 1988 they published their results in the American Journal of Physics. The paper described a wormhole geometry that was, in principle, stable enough to be traversed a tunnel through space-time with two mouths connected by a throat, held open by a quantity of exotic matter concentrated at the throat. Without the exotic matter, the throat would collapse. With it, the geometry could be maintained long enough for a traveler to pass through. Sagan used the wormhole idea in Contact, and Thorne went on to other remarkable achievements. In 2017, he shared the Nobel Prize in Physics as one of the founders of the LIGO project, which made the first direct detection of gravitational waves on September 14, 2015 waves, produced by two merging black holes, approximately 1.3 billion light-years away. Ripples in the fabric of space-time, so small that they produce displacements thousands of times, smaller than a proton, but detectable nonetheless by the most sensitive instruments ever built. The announcement came on the 11th of February 2016 and was one of the most significant physics results of the 21st century. Thorne is not a speculative thinker on the fringes of the field. His work on traversable wormholes was serious general relativistic calculation, done by one of the most respected relativists in history. The result was that traversable wormholes require exotic matter with negative energy density, in amounts that appear to be macroscopic and concentrated at the throat. The same exotic matter problem that plagues the Alcubierre drive afflicts the wormhole. Without it, you have an unstable mathematical curiosity. With it, you have an object that should be physically maintained, but the exotic matter does not appear to exist in the required form. Thorne went further, into territory that connects wormholes directly to time travel. He showed that a traversable wormhole could be converted into a time machine through a procedure that is, once you understand it, almost elegantly simple. Take a traversable wormhole with two mouths, one at each end of the tunnel. They initially exist at the same moment in time, connected by the shortcut of the throat. Now take one mouth and accelerate it to a velocity close to the speed of light, travel it around in a large loop, and bring it back to its starting location. According to special relativity, the accelerated mouth ages less than the stationary mouth during this journey. Relativistic time dilation. The mouth that traveled has experienced less time. Now the two mouths, which are still physically connected by the wormhole throat, exist at the same location in space, but at different times. Enter the older mouth, and you emerge from the younger mouth at an earlier time. The traversable wormhole has become a time machine. This is not Thorne speculating wildly. It is the direct application of special relativity's time dilation, a phenomenon confirmed by atomic clocks on airplanes and by GPS satellite corrections to the geometry of a traversable wormhole. The physics at each step is solid, time dilation is real and measured, traversable wormholes are mathematical solutions to the field equations, and their combination produces backward time travel as a logical consequence. John Wheeler coined the term wormhole in 1957, borrowing the image of a worm tunneling through an apple. Rather than traveling across the surface from one side to the other, the worm takes a shortcut through the interior. Wheeler spent much of his later career thinking about the nature of space-time at extremely small scales, at what physicists call the Planck scale, a length of approximately 1.616 times 10 to the power of negative 35 meters. So small that the smooth fabric of space-time as described by general relativity would, according to some theoretical arguments, break down into a roiling, frothing foam of quantum geometry. Wheeler called this concept space-time foam, and he proposed that at this scale, tiny virtual wormholes would be constantly forming and dissolving as part of the quantum vacuum fluctuations of geometry itself. This is a beautiful theoretical concept, but it describes physics at scales roughly 20 orders of magnitude smaller than an atomic nucleus, far beyond any current or foreseeable experimental probe. Stephen Hawking, whose contributions to the study of black holes and cosmology are legendary, addressed the time travel implications of traversable wormholes directly in a 1992 paper in Physical Review D, on Mao, where he proposed what he called the chronology protection conjecture. The conjecture states that the laws of physics conspire to prevent the formation of closed time-like curves, the paths through space-time, that loop back to their starting point in time, making the universe safe for historians. As Hawking put it with characteristic wit, his argument was based on the calculation that, as a space-time geometry approaches the formation of a closed time-like curve, the energy density of quantum vacuum fluctuations diverges, goes to infinity in a way that would likely destroy the geometry before the causal loop could form. Hawking was characteristically direct about his reasoning, asking rhetorically why, if time travel to the past were genuinely possible, we had not been visited by tourists from the future. The absence of such visitors was, in his view, strong circumstantial evidence that time travel is impossible, and his chronology protection conjecture was the theoretical mechanism he proposed to explain that absence. If closed time-like curves cannot form because quantum effects always destabilize them first, then the ban on visitors from the future follows automatically. The important caveat is that the chronology protection conjecture remains a conjecture. It has not been proven. The calculations that support it are compelling but incomplete. They require a full theory of quantum gravity to be conclusive, and a complete and consistent theory of quantum gravity does not yet exist. The chronology protection conjecture is the most physically plausible barrier against time travel currently available, but it is a hypothesis, not a theorem. Kurt Gödel, the mathematician who proved the incompleteness theorems that shook the foundations of mathematics in the early 20th century, discovered in 1949 that Einstein's field equations admit solutions, describing a rotating universe in which closed time-like curves are a feature of the global space-time structure. In a Gödel universe, it would be possible, in principle, to travel into the past simply by following a sufficiently large closed spatial loop. Our universe does not appear to have the rotation required for the Gödel metric to apply, so this particular avenue to time travel is not relevant to our cosmos. But Gödel's discovery established once and for all that general relativity's equations, taken at face value, do not independently forbid time travel. The equations permit geometries with causal loops. Whether nature actually permits such geometries to form is a separate question, one that Hawking's conjecture addresses but does not definitively settle. Let us now step back from specific mechanisms and spend time with the broader physics of why the speed of light is what it is, because understanding that helps clarify why no engineering trick, no matter how clever, is going to get around the causality constraint. The speed of light is not arbitrary. It is not a parameter that was set at 299,792,458 meters per second by some cosmic dice roll. It emerges from the structure of electromagnetism, from the relationship between the permittivity of free space, a measure of how much electric field energy can be stored in the vacuum, and the permeability of free space, the corresponding magnetic quantity. The speed of light equals 1 divided by the square root of the product of these two constants. Both constants are measurable and have been measured to high precision. Their product uniquely determines c, and c is therefore not a free parameter of the theory. It is a consequence of the electromagnetic structure of the vacuum. General relativity promotes c to a more fundamental role. Still, in Einstein's theory of gravity as space-time geometry, c is not just the speed of electromagnetic waves. It is the slope of the light cone in space-time geometry. It is the rate at which gravitational disturbances propagate. It is the speed at which a gravitational wave travels from its source to a detector. The LIGO detection of gravitational waves on the 14th of September 2015 confirmed that gravitational waves travel at the speed of light with extraordinary precision. And the 2017 multi-messenger event designated GW 170817, which was the first detection of both gravitational waves and electromagnetic radiation from the same source. Two neutron stars, merging in a galaxy 130 million light-years away, measured the relative speed of gravitational and electromagnetic waves and found them consistent with C2 within a few parts in 10 to the power of 15. The speed of light governs not just electromagnetism, but the propagation of gravitational information through the fabric of space-time itself. What would change if C were different? If it were twice as large, the fine structure, constant a dimensionless number, approximately equal to 1 over 137, that governs the strength of electromagnetic interactions, and therefore the structure of atoms. The energy of chemical bonds and the character of chemistry would be different. Atoms would have different sizes. Chemical reactions would have different energetics. The temperature and luminosity of stars, which depend on nuclear physics and electromagnetic radiation, would change. The world would not merely be inconvenient. It would be a physically different kind of world, and whether it could contain anything resembling biological life is genuinely unclear. If c were infinite, if there were no limit on signal propagation speed, as was assumed in Newtonian mechanics, causal structure would be absent from the universe. Every event would be in the past light cone of every future event, and in the future light cone of every past event. There would be no space-like region, no causally disconnected events. Information about everything would in principle be available everywhere simultaneously, and the concept of a locally distinct present, of a unique set of events that can causally influence a given moment without any delay, would not exist. The thermodynamic arrow of time, which depends on causal structure for its foundation, would have no basis. The meaningful directionality of time, the fact that memory works, that entropy increases, that causes precede effects, emerges from the finite value of c and the light cone structure it defines. The twin paradox is the most human-scale illustration of what special relativity's speed limit actually does to the experience of time, and it deserves extended treatment because it is so counterintuitive and so thoroughly confirmed by experiment. The thought experiment goes back to Paul Langevin, a French physicist who presented it in a 1911 lecture that electrified its audience. Langevin's version involved a traveler who journeys to a distant star at a velocity close to the speed of light, then returns. The traveler, moving at near c relative to Earth, experiences time dilation. Their clocks run slow, their heartbeats slow, their metabolism slows. Every physical process in their body and their ship slows down relative to the clocks and heartbeats and metabolisms of people who remained on Earth. When the traveler returns, they are younger than those who stayed behind. 2 years might have passed for the traveler, while a century passed on Earth. The counterintuitive element, the thing that makes it feel like a paradox rather than a simple consequence of relativity, is this. In special relativity, all motion is relative. From the traveler's perspective, it is the Earth that is moving away and then returning. So why is it not the Earth-bound people who are younger? The resolution is that the situation is not symmetric. The traveler must accelerate, first to reach near-sea velocity, then to decelerate and stop at the destination, then to accelerate again for the return trip, then to decelerate and stop at Earth. Acceleration is not relative. In the same way that constant velocity is, you can feel it, measure it with an accelerometer, and it breaks the symmetry between the two twins. When the detailed calculation is performed using the correct relativistic treatment of the accelerating frames, it gives an unambiguous answer. The traveler is younger. This is not a theoretical construct awaiting experimental confirmation. It has been directly tested. In October of 1971, physicists Joseph Hafele and Richard Keating loaded very precise atomic clocks onto commercial aircraft and flew them around the world, once eastward and once westward, then compared the clocks to stationary atomic clocks at the United States Naval Observatory in Washington. The effects of both special relativity, velocity time dilation, and general relativity gravitational time dilation, which causes clocks at higher altitude to run slightly faster, were predicted in advance. When the planes returned and the clocks were compared, the results matched the relativistic predictions to within experimental uncertainty. Time dilation is real, measurable, and consistent with theory. GPS satellites offer a continuous, operationally critical demonstration of the same physics. Each GPS satellite orbits at an altitude of approximately 20,200 kilometers, moving at roughly 14,000 kilometers per hour. At that altitude, gravity is weaker, which by general relativity makes clocks tick faster by about 45 microseconds per day. At that velocity, special relativistic time dilation makes clocks tick slower by about 7 microseconds per day. The net effect is that GPS satellite clocks gain approximately 38 microseconds per day relative to ground-based clocks. If the satellite's computers did not continuously correct for this effect, the position estimates that GPS provides would drift by approximately 10 kilometers every day, according to NASA's analysis. Every phone navigation app, every precision agriculture system, every military guidance system using GPS is relying on Einstein's relativity to stay accurate. The physics is not academic, it is in your pocket. Muons from cosmic rays provide a third and particularly elegant confirmation. When high-energy cosmic ray particles, protons, mostly, arriving from deep space strike molecules in Earth's upper atmosphere, they produce, among other things, a particle called the muon, which is essentially a heavier version of the electron. Muons are unstable. They decay with a half-life of about 2.2 microseconds into an electron and 2 neutrinos. Given a typical altitude of creation in the upper atmosphere of about 15 kilometers, and a typical speed close to c, a non-relativistic calculation says almost no muons should survive the journey to sea level. The time required to travel 15 kilometers, even at nearly c, is several times the muon's half-life. Most of them should decay long before reaching the ground. And yet ground-level detectors see large numbers of muons from cosmic rays. The reason is time dilation. From Earth's reference frame, the muon's internal clock, its decay clock, runs slow by a large Lorentz factor because the muon is moving so close to c. From the muon's own reference frame, the distance to Earth's surface is contracted by that same Lorentz factor. Either way, the muon covers the distance in a small enough fraction of its proper lifetime to survive. The number of muons reaching ground level matches the predictions of special relativity precisely. This experiment, in various forms, has been run many times and has never produced a result inconsistent with relativity. The precision to which special relativity has been tested through systematic searches for violations of Lorentz invariance is almost incomprehensible in its thoroughness. Lorentz invariance is the mathematical symmetry at the heart of special relativity, the symmetry that says the laws of physics are the same at all speeds and in all directions. Tests using atomic clocks, ticking in different orientations and at different velocities, have searched for direction-dependent or velocity-dependent variations in the rate of atomic transitions. Tests using particle accelerators have searched for energy-dependent modifications to the relationship between a particle's energy and its velocity. Tests using gamma rays from distant gamma-ray bursts have searched for energy-dependent variation in the speed of photons, which some quantum gravity theories predict at very high energies. All of these tests have come up empty. No violation of Lorentz invariance has been detected at any energy scale from laboratory chemistry up to the highest energy cosmic rays ever measured. The sensitivity of these experiments is extraordinary. They have probed for deviations from special relativity down to energy scales approaching the Planck scale, which is 1.22 times 10 to the power of 19 GeV, 18 orders of magnitude beyond the reach of the LHC. The universe has been interrogated with enormous diligence, and its answer is consistent. Special relativity holds, the speed of light is the limit, and Lorentz invariance is intact. Now let us spend time on what causality violation would actually mean in practical terms beyond the abstract mathematics. Because it is easy to hear causality violation as a technical phrase rather than as what it actually describes, which is the complete destruction of the logical coherence of the universe. Causality is the principle that causes precede their effects. It is so fundamental to human experience and human reasoning that it is difficult to articulate how basic it is without sounding like you are stating the obvious. Of course, causes come before effects. What would it even mean for an effect to precede its cause? But special relativity's analysis of FTL travel forces us to confront that question directly, because in certain reference frames associated with FTL signals, effects do precede their causes. The mathematics is unambiguous. Consider what causality actually underlies. Every scientific experiment relies on it. The data you collect is the effect of the experimental arrangement you established first. And the causal relationship between arrangement and data is what makes the data meaningful as evidence. Every medical treatment relies on it. The drug was administered before the disease retreated, and the causal relationship between administration and retreat is what makes the treatment useful. Every engineering project relies on it. The bridge stands because the steel was placed before the load was applied. And the causal relationship between construction and bearing capacity is what makes engineering a science rather than a lottery. Every judicial system relies on it. A defendant is responsible for an outcome only if their action preceded and caused it. Every memory relies on it. The present state of your neurons is caused by past experience, and the temporal order experience first. Memory, second, is what makes memory a record of the past, rather than a random mental state. If FTL travel broke causality in the way the mathematics demands, not in a marginal quantum edge case way, but in the clean, observer-accessible way of the tachyonic antitelephone, then the causal relationships underlying all of these activities would be reference frame dependent. For some observers, cause and effect would be ordered one way. For others, they would be ordered the opposite way. There would be no fact of the matter, independent of observer velocity, about which came first. The scientific method, which requires that experimental results be reproducible and unambiguous and independent of the velocity of the lab, would break down at its foundation. Consider the thermodynamic dimension of this. The second law of thermodynamics, one of the most robustly confirmed laws in all of physics, states that the entropy of a closed system, a measure of its disorder, its unavailability of useful energy always increases or remains constant over time. Hot coffee cools down, cold coffee never spontaneously heats up. A broken egg does not reassemble itself. A drop of ink diffusing through water does not spontaneously concentrate again. These processes are irreversible, and their irreversibility defines the thermodynamic arrow of time. The direction in which entropy increases is the direction we call forward in time. The The second law is statistical. It is not that entropy-decreasing processes are impossible in a fundamental sense, but that they require the coordinated reversal of the motion of every molecule in the system, which is so astronomically improbable that it never happens spontaneously. But here is the link to causality. The statistical argument for the second law depends on the causal structure of time. Molecules bounce around randomly, with no coordinated direction, precisely because each collision is caused by the prior state of the molecules, which was caused by the state before that, and so on back to some low-entropy initial condition. The second law works because causes precede effects, and because the microscopic degrees of freedom in a large system become decorrelated as time passes in the forward direction. If causes could follow effects, if the causal direction of time were not fixed, the thermodynamic argument for the second law would dissolve, and with it, the one directionality of time that underlies our entire experience of the universe. The CPT theorem, a fundamental result in quantum field theory, states that the combined transformation of charge conjugation, parity reversal, and time reversal leaves physical laws invariant. This is a symmetry of the deep equations of physics, confirmed experimentally by the detailed behavior of subatomic particles. But the theorem involves all three transformations together. Individual time reversal is not a symmetry. CP violation, first discovered in the decay of K-mesons in the 1960s and subsequently observed in B-mesons and other systems, means that the universe has a weak but real preference for a particular direction of time built into its fundamental interactions. The universe's arrow of time is not just a statistical artifact of large numbers of molecules. It is partially encoded in the physics of elementary particles. Faster than light travel, by potentially allowing backward time causal influences, would run headlong into this asymmetry in ways that are not fully understood, but are certain to create profound inconsistencies. Let us now address something that the science fiction tradition has gotten very wrong in a very seductive way: the portrayal of FTL travel as liberating, as the thing that opens the universe up, as the key to a future that is better than our present, because we can finally reach what we can see. This narrative is emotionally compelling, and I want to honor the genuine longing that underlies it before explaining why it is backwards. The longing for FTL is the longing for more space, more time, more contact with whatever might be out there among those 2 trillion galaxies. The observable universe spans approximately 93 billion light-years in diameter, a number made larger and more mind-bending by the fact that it is not the distance light has traveled since the Big Bang. The universe is about 13.8 billion years old, but the distance of the most remote objects we can see, their original distances inflated enormously by the expansion of space over those 13.8 billion years. Within this observable volume, a 2016 study published in the Astrophysical Journal revised the count of galaxies upward to approximately 2 trillion. 2,000 billion galaxies, the vast majority of which we will never visit at sublight speeds within any individual human lifetime or any individual civilization's lifetime, because the distances are simply too enormous. The Milky Way, our own galaxy, contains somewhere between 100 and 400 billion stars, and the nearest star system to our own, Alpha Centauri, is approximately 4.2 light-years away. At the fastest speeds achieved by any human-made object, the Voyager 1 spacecraft, now the most distant human-made object ever built, moving at about 17 kilometers per second, it would take approximately 75,000 years to reach Alpha Centauri. The nearest galaxy is about 2.5 million light-years away. The scales are genuinely staggering. So the longing for FTL is understandable. Of course, a species that can see the stars wants to reach them. Of course, the light-years feel like an insult. Of course, the obvious response to being capable of looking across 93 billion light-years of universe and seeing 2 trillion galaxies of stars and wanting desperately to explore them is to feel that the physics is being unnecessarily cruel. The frustration is legitimate, the aspiration is beautiful, and none of that changes the physics. The Fermi paradox is relevant here. though it does not prove anything by itself. The paradox, named for Enrico Fermi, who reportedly raised the question at a lunch discussion at Los Alamos National Laboratory in 1950, is the apparent tension between the large number of stars in the universe and the age of the universe on one hand, and the complete absence of confirmed contact with or detection of extraterrestrial civilizations on the other. Given the billions of years available, even sublight interstellar travel should have allowed a sufficiently motivated civilization to spread across the galaxy in a few tens of millions of years. A blink in cosmic time. Where is everybody? One of the most frequently invoked candidate resolutions is that FTL travel is genuinely impossible, and that sublight travel is slow enough that interstellar colonization, though technically achievable, proceeds so slowly that its consequences are not yet visible to us. If every civilization is limited to sublight speeds, the distances between stars are a genuine barrier that contains and isolates civilizations. Civilizations live and die without their influence propagating far beyond their home systems, and the silence of the cosmos becomes comprehensible rather than mysterious. This resolution does not prove that FTL is impossible, but the silence of the cosmos is at least consistent with that conclusion. Now, let us spend time thinking about what the universe would have to be like for FTL to be possible without breaking causality. Because some people have proposed that perhaps there is a version of FTL that is causal, that does not permit the construction of tachyonic antitelephones or warp drive time machines. This is a real research program in certain corners of theoretical physics, and it deserves a serious response. The most natural version of this proposal involves modifying special relativity so that there is a preferred reference frame, an absolute rest frame, in which FTL signals travel from source to destination without the time reversal effect that occurs in other frames. If there is a preferred frame, then the argument that FTL implies backward time travel in some frames fails, because not all frames are equal. There is one frame in which the time ordering of events is physically real, and FTL signals in that frame do not reverse time, even though they appear to reverse it in other frames. The problem with this approach is that no preferred frame has been detected. The Michelson-Morley experiment and a century of subsequent experiments testing Lorentz invariance with ever-increasing precision have found no trace of a preferred frame. If a preferred frame exists, its effects on measurable physical quantities must be smaller than the sensitivity of any experiment ever conducted, which means they must be utterly negligible for any practical purpose. A theory that introduces a preferred frame to save FTL, while making that frame observationally indistinguishable from a theory with no preferred frame, is not a falsifiable scientific proposal in any operational sense. Some versions of quantum gravity, particularly certain approaches to loop quantum gravity and causal set theory, introduce structures that could be interpreted as a preferred causal ordering of events. But these theories are constructed precisely to be consistent with the observable predictions of special relativity at accessible energy scales, which means their departures from Lorentz invariance are at energy scales far beyond any current probe. Whether they genuinely permit FTL information transfer without causality violation is not established, and the theories themselves are not complete enough to provide a definitive answer. The most honest statement is this: no currently known physics provides a mechanism for FTL travel or FTL information transmission that does not, upon careful analysis, either require exotic matter that does not exist, violate causality in the way the tachyonic antitelephone illustrates, or require modifications to special relativity so small as to be undetectable by any instrument available now or foreseeable in the near future. The dream of FTL is not supported by physics. It is supported by longing, which is real and human and worth acknowledging. But longing and physics are different things. There is also a deep connection between the FTL prohibition and the nature of information, one that goes beyond the specific no-communication theorem for entanglement and reaches something more fundamental. Information, in the precise sense used by physicists and information theorists, is the physical difference between one state of a system and another, whether the switch is on or off, whether the particle is here or there, whether the message says yes or no. Shannon, information theory, developed by Claude Shannon at Bell Labs, beginning in 1948, provides the mathematical framework for quantifying information, and the framework is entirely agnostic about physical substrate. A bit is a bit, whether it is stored in a transistor, a neuron, or the spin of a particle. What Shannon's framework assumes, without stating it explicitly, is causal order. The bit is encoded at one time and decoded at another, later time, and the later time comes after the earlier time, and the information travels from encoder to decoder at some finite speed. This temporal and causal ordering is not a feature of Shannon's mathematics. It is a precondition for the mathematics to have physical meaning. The concept of communication requires a sender, a receiver, a message, and a time ordering, message sent, message received, with sent before received. If FTL communication made the time ordering reference frame dependent, the concept of communication, and by extension, the concept of information itself, as a physical quantity, would lose its frame-independent meaning. This is perhaps the most fundamental way in which FTL would destroy reality, not by tearing space-time apart, not by creating grandfather paradoxes that logic cannot resolve, but by making information meaningless as a physical quantity. In a universe where the time ordering of sending and receiving is not universally agreed upon, there is no physical fact about whether information was transmitted at all. The concept of knowledge, of one physical system coming to represent the state of another through a causal interaction, would dissolve. And without knowledge, without the possibility of one physical system encoding information about another in a causally ordered way, the universe is not just strange or paradoxical, it is incoherent. It is noise without signal, events without meaning, physics without physics. Consider what the act of measurement, the most fundamental operation in experimental science, requires. A measurement is an interaction between a measuring device and the system being measured, in which the device's state becomes correlated with the system's state. The correlation was caused by the interaction was caused by the physical setup of the experiment, and the experimental setup was established in the past, before the measurement was made. The causal chain, experimental design, precedes, setup, precedes, interaction, precedes, measurement, precedes, data, is the chain that makes experimental results meaningful as evidence. Break causality, and that chain breaks. The data you collect is no longer evidence about the system you measured, because the causal relationship between measurement and data is not frame independent. Your laboratory result might be, in some valid reference frame, the cause of the experiment rather than its effect. This is not hyperbole or philosophical extrapolation. This is the direct logical consequence of combining FTL information transfer with the Lorentz transformations of special relativity. The people who wrote the tachyonic antitelephone paper in 1970 were doing physics, not philosophy, and the conclusion is as solid as the Lorentz transformation itself. Let us now make the distinction that is sometimes missed between the impossibility of FTL information transfer and the existence of phenomena that superficially resemble FTL but are not. There are several real physical phenomena that are sometimes described, misleadingly, as faster than light, and it is worth going through them carefully, both to correct the misconceptions and to understand what they tell us about the nature of the speed limit. The phase velocity of light in a medium is one example. Light, traveling through water, moves at approximately 225,000 kilometers per second, about 75% of c, because the electric fields of the photons interact with the electrons in the water molecules in a way that slows the propagation of the wave's phase. But under some exotic conditions, in certain materials with very specific optical properties, called anomalously dispersive media, the phase velocity of a light wave can exceed c. This sounds alarming, but the phase velocity is not the velocity at which information travels. The group velocity, the velocity at which the envelope of a wave packet, and therefore the information encoded in that packet, travels, is always limited by c. The phase of a wave is a mathematical feature. The information content rides the group. You cannot send a message faster than the group velocity, and the group velocity is bounded by c. The Hartmann effect, observed in quantum tunneling, is another example. When a quantum particle tunnels through a barrier, the tunneling time appears, in certain measurements, to be shorter than the time light would take to travel the same distance, suggesting apparent FTL transit. This effect was measured in experiments with microwave photons tunneling through undersized waveguides and with electrons tunneling through semiconductor barriers. But careful analysis shows that no information is transmitted faster than light during tunneling. The tunneling time measurements are subtle and interpretation dependent, and the signal front, at the first change in the transmitted field that constitutes new information, never arrives faster than c. The Hartmann effect is a quantum weirdness, not an FTL signal. The expansion of the universe, discussed earlier, carries distant galaxies away from us at recession velocities exceeding c, but this is space-time expansion, not local motion through space-time. The distinction matters because no information encoded in those distant galaxies can ever reach us if the galaxies are beyond the cosmic event horizon, the boundary beyond which light can never reach us given the universe's accelerating expansion. The recession velocity exceeds c, but the information transfer is zero because the light carrying the information cannot outrun the expansion. The universe's own expansion demonstrates both that space-time can move faster than c and that this does not enable FTL communication. Quantum wave function collapse appears, in one interpretation of quantum mechanics, to happen instantaneously everywhere when a measurement is made. The wave function of a particle extends across space, and when you measure the particle here, the wave function collapses everywhere simultaneously. But no information is transmitted by this collapse, because the outcome is random and uncontrollable. There is nothing in the collapse that a distant observer could use to receive a message, because the only thing that changed instantaneously was the probability distribution of what they would find when they made their own measurement, and that probability distribution is not accessible until they actually measure, and the comparison of their result to yours requires a classical channel. Wave function collapse, in all the interpretations that preserve causality, is either non-local but information-free, or local and deterministic, as in many worlds, or observer-relative in a way that does not allow superluminal signaling. Wheeler and Feynman's absorber theory of electrodynamics, developed in the 1940s, uses advanced waves solutions to Maxwell's equations that travel backward in time as a computational tool for calculating electromagnetic interactions. In this formalism, an electron emitting radiation sends both a retarded wave forward in time and an advanced wave backward in time, and the observable radiation is a combination of contributions from all other electrons in the universe absorbing the retarded wave. This is a genuinely unusual formalism, and the backward in time waves are part of the calculation, but the observational predictions of absorber theory are identical to those of conventional electrodynamics, with no net backward in time effects visible in any measurement. The advanced waves are internal to the mathematical machinery and cancel out in the final physical predictions. They do not represent real FTL information transfer. String theory, the leading candidate for a unified theory of all fundamental forces, has been analyzed extensively for its causal properties. The theory respects Lorentz invariance and causality in its perturbative formulation, and there is no known mechanism within string theory for FTL information transfer. Some non-perturbative aspects of string theory involve objects called D-branes and dualities between different string theories, but again, the causal structure of observable physics is preserved. Loop quantum gravity, causal dynamical triangulations, and causal set theory. The other leading approaches to quantum gravity are either explicitly built to preserve causal structure or are still incomplete enough that their causal implications are not fully understood. The unified message from all of these approaches is that the more deeply we dig into the structure of physics, the more firmly causality is embedded. It is not an accident of the particular theory we happen to have. It is a feature that every consistent extension of our current physics has preserved, and that every failure to preserve it has produced not a better theory, but a worse one, full of inconsistencies and paradoxes. Now let us revisit the human dimension of this story, because it is easy to get lost in the physics and lose sight of what it means for the oldest and deepest of human aspirations. Humanity has been watching the stars for the entire span of recorded history, and almost certainly long before. The oldest surviving astronomical records from Mesopotamia and Egypt are thousands of years old. The recognition that the stars are suns, that they are distant, and that they might have planets of their own, a recognition that was only fully established in the last century, transformed the relationship between humanity and the cosmos from one of observation to one of potential. Kinship. We are not unique in being made of atoms. The atoms are everywhere. We are not unique in existing on a rocky planet. There are billions of rocky planets. We are not unique in orbiting a medium-sized star. There are hundreds of billions of such stars in our galaxy alone. The logical inference that life and perhaps intelligence might exist elsewhere in those 2 trillion galaxies is one that haunts the imagination. End quote. And the distance to even the nearest star is 4.2 light-years. At the speed of the fastest rocket ever built, that is 75,000 years. At a meaningful fraction of c, obtainable in principle by future technology, it would be a decade or so for the crew, thousands of years for Earth. The distances are not just challenging. They are existentially isolating in a way that the size alone does not convey, because even at sea, travel between the stars takes years, between galaxies, millions of years, between clusters of galaxies, billions of years. The universe contains, in principle, more than we could ever know, more than we could ever visit, more beauty and complexity and variety than any one civilization could fully explore in any span of time, less than the age of the universe itself. And the speed of light ensures that we can only ever reach a tiny fraction of it. Not because we are not smart enough, not because we are not advanced enough, but because the geometry of space-time and the causal structure that geometry enforces simply does not permit us to be everywhere at once. We are local, causal creatures in a local, causal universe, and the light cone is the shape of our reach. That constraint, once understood, reshapes the longing for FTL into something slightly different. The question is not, how do we go faster? The question is, what is the right relationship between intelligence and the universe it inhabits, given the physics that governs both? And the answer that physics suggests is humility, a recognition that the universe is not arranged for our convenience, that its structures exist for reasons deeper than our desires, and that the most productive response to a constraint that cannot be removed is to understand it deeply rather than to resist it futilely. The physics that forbids FTL is the same physics that makes us. The fine structure constant, which is set by C, and the structure of electromagnetism determines the size of atoms and therefore the character of chemistry. Chemistry produced biology. Biology produced intelligence. Intelligence produced the question of why you cannot go faster than the speed of light. The answer to that question traces back to the same physical constants that made the questioner possible. The speed of light is both the limit and the precondition. You cannot have the beings who want to exceed it without the physics that forbids it. This is not mysticism. It is a statement about the interconnection of physical constants and the structures they produce. If C were different, atoms would be different, chemistry would be different, stars would be different, and the universe that resulted would be different in ways that may or may not support the development of intelligence. The universe we actually live in, the one with C at 299,792,458 meters per second, with the fine structure constant at approximately 1/137, with hydrogen as the most abundant element and nuclear fusion as the energy source of stars, is the universe that produced us. The constraints it places on travel are part of the same package as the opportunities it provides for existence. Richard Feynman, one of the most intuitive physicists of the 20th century and one of the most effective teachers of physics who ever lived, observed that the thing which does not fit, the anomalous result, the measurement that breaks the pattern, is the most interesting thing in science. This is true. The history of physics is a history of following the anomalies. The failure to detect the ether led to special relativity. The ultraviolet catastrophe in blackbody radiation led to quantum mechanics. The precession of Mercury's perihelion was the anomaly that pointed toward general relativity. Every fundamental advance in physics began with something that did not fit. But Feynman's insight assumes a universe where things do or do not fit, where patterns exist and can be broken, where results are reproducible and distinguishable from background. All of that requires causality. The anomaly that does not fit is meaningfully distinct from the expected result, only if the expected result was expected because of causal reasoning about the experimental setup, and the anomaly was detected because its effect came after its cause in a consistent, observer-independent temporal ordering. Science, as a method for generating knowledge, requires causality as a precondition. The value of the anomaly depends on the reliability of the causal framework in which it is embedded. Break causality, and there are no more anomalies, because there are no more patterns against which anomalies can be distinguished. Let us also think carefully about what faster-than-light travel would mean for the concept of personal identity, which is a somewhat unusual angle on the problem, but illuminates something important. The sense in which you are the same person you were yesterday depends on causal continuity. The neurons in your brain today are in the states they are in because of the states they were in yesterday, and the states they were in yesterday were caused by the experiences you had, and the experiences you had were caused by events in the world. And the chain of causation connecting today you to yesterday you is unbroken and forward-pointing in time. Memory is causally stored experience. Personality is causally accumulated habit. Identity is the pattern that causality preserves across time. In a universe with causality violation, this continuity would be fragile in a way that goes beyond any normal threat to personal identity. It would not be that you might forget, or change, or be confused. It would be that the causal chain constituting your identity would have no reliable temporal direction. Events from your future could, in principle, be causing events in your past. The FTL signals threading through the tachyonic anti-telephone logic could be running in both temporal directions simultaneously. The narrative of a self moving through time from birth to death would not just be difficult to maintain, it would have no physical basis. The you of 10 years ago might be causally downstream of the you of today through some chain of FTL interactions. Personal identity in a causality-violating universe is not just philosophically problematic, it is physically undermined. This is perhaps the most viscerally concrete way to understand what causality violation would mean for lived experience. Not the abstract annihilation of scientific inference, not the formal breakdown of thermodynamics, but the erasure of the thread connecting who you were to who you are to who you will become. The self is a causal structure threading through time. Cut causality, and you cut the self. The universe with FTL is not a universe in which people travel faster. It is a universe in which the concept of a person, as a being, with a history and a future connected by causal continuity, is no longer available. Let us now take stock of where we are. We have established that special relativity, tested with extraordinary precision in every particle accelerator and atomic clock and cosmic ray measurement ever conducted, forbids faster-than-light travel for any object with mass. We have established that this is not an engineering barrier but a mathematical singularity. Infinite energy would be required to reach C, and infinite energy is not achievable by any finite process. We have established that FTL information transfer, even without physically moving a massive object, implies backward-in-time signaling in some reference frames through the clean and unavoidable mathematics of the Lorentz transformation. We have established that backward-in-time signaling implies the possibility of causal loops through the tachyonic antitelephone, and that causal loops produce logical contradictions with no consistent resolution. We have established that the Alcubierre drive and traversable wormholes, the two most seriously studied FTL proposals from within physics, both require exotic matter with negative energy density that has never been confirmed to exist, and both, upon analysis of their causal structure, permit the construction of closed time-like curves. We have established that quantum entanglement, though genuinely non-local in a narrow sense, cannot transmit information FTL because of the randomness of measurement outcomes and the no communication theorem. We have established that every apparent FTL phenomenon in real physics phase velocity exceeding c in anomalous media, the Hartmann tunneling effect, the recession of distant galaxies, wave function collapse involves no actual FTL information transfer when examined carefully. The conclusion that emerges from all of this, from every direction of analysis, is not that FTL is merely very hard. It is that FTL information transfer is incompatible with a universe that has consistent causal order, and causal order is the property that makes the universe a universe rather than chaos. The speed of light is not one physical constant among many, important, but in principle adjustable. It is the slope of the light cone in space-time geometry, the boundary of causality, the constraint that makes before and after have physical meaning for physical interactions, and the parameter that makes the concept of physical law of reliable, reproducible, causally ordered relationships between events possible at all. When physicists say that FTL would violate causality, they sometimes say it in the shorthand way that professionals use among themselves, in a way that sounds like a technical objection rather than an existential one. What it actually means is this: a universe with FTL would not be a universe in which physics is different. It would be a universe in which the concept of a consistent history of a sequence of events with definite temporal order caused by prior events and causing subsequent ones no longer applies. It would be a universe in which science is impossible, not because the laws are different, but because the category of law is undermined. It would be a universe in which knowledge, memory, and personal identity have no reliable, physical basis. It would be a universe in which the concept of universe, of a consistent, unified, causally ordered whole, is dissolved into something for which we do not have a word, because we have never needed one. Faster than light travel would not take us to the stars. It would take us to a place that cannot be mapped, cannot be navigated, and cannot be occupied by anything that carries a consistent history. The universe drew a line at 299,792,458 meters per second, and it drew it not as an obstacle, but as a definition. This is where cause ends and noise begins. The aspiration to cross that line is one of the most human things there is. The physics preventing it is one of the most fundamental things there is. And understanding deeply and clearly why those two facts are what they are is the closest we can get to wisdom about the particular kind of universe we are lucky enough to inhabit. The stars are still there. They are still beautiful. They are still, in some important sense, worth reaching toward. Whether we reach them in generation ships crossing the dark over thousands of years, or in radio signals carrying our voices across the light years at exactly the speed that the structure of space-time allows, or simply in the act of looking up at night and understanding, a little more clearly than before, what we are looking at and why it is so far away. The distance is not the cruelty. The distance is the measure of how large a universe physics could build while keeping it coherent. And a coherent universe, a universe with a past and a future, with causes and effects, with memory and science, and the possibility of knowledge, is a gift that the speed of light buys for us at the price of the stars. That price is steep, and it is the only price at which a universe worth inhabiting can be had.